Section 6.2, Regions Between Curves. In Chapter 5, we looked at the area that was underneath a curve and the area bounded between a curve and the x-axis. Now we're going to look at the area that is trapped between two functions. So let's consider the area between y equals f of x and y equals g of x, where y equals f of x is the function on top, or the upper function, and g of x the one on the bottom, or the lower function. So we're going to start out by trying to approximate that area by looking at rectangles where we chop up the interval from a to b into n subintervals. So they've got one of those subintervals highlighted, and we're going to focus on that one and try and find the area for that a sub k. So to do that, since it's a rectangle, we just want to do height times width. And then how do you get the height? Well, the height would be from the top of the rectangle down to the bottom, so whatever this vertical distance is. So you'd want to take the y value from the top and subtract the y value from the bottom. So we're going to do height is top minus bottom. And then the width is just going to become delta x from the subintervals. And then again, how do you get that top? You do the height of the top function. So you take an x sub k star and you plug that into f of x, and that would give you the top height. And then you look at the bottom height comes from plugging x sub k star into the bottom function or lower function. So that'll be g of x sub k star. So when you subtract the top function minus the bottom, you get the height. Multiply that by the width, delta x, and you're coming up with an area for just that one rectangle. So then the idea is, if you want the area of the full region, you add up the area of all n of those rectangles by doing height times width all the way across. And so that ends up becoming the sum, as k goes from 1 to n, of just what we wrote up above. So f of x k star top minus g of x sub k star, that's the bottom, times delta x. And that would still be just an approximation if we did n rectangles. So if we take the limit as n goes to infinity, we can convert that over to exact area. So let's look at that now. The area of a region between two curves. Suppose f and g are continuous with f of x greater than or equal to g of x, which is to say f of x is higher, so therefore the top function, on the interval a to b. The area of the region bounded by the graphs on that interval from a to b is given by the limit as n goes to infinity of the sum as k goes from 1 to n of f of x k star minus g of x k star for the heights times delta x for the widths. And when you do that, the limit as n goes to infinity of the sum becomes our definite integral from a to b. And then we end up converting those just to f of x minus g of x inside. When you go to the integral, you don't need the k star anymore. And then that delta x becomes dx. So that's going to be our integral. And it's good to write that in terms of words, not just in terms of functions. So this would be the integral from a to b of the top minus the bottom to give us the height times dx, but that dx represents the width. So I find it useful to remember these formulas in terms of their words, and then we can work out the rest. So it's the integral from a to b of height times width, or top minus bottom times dx. Don't get hung up on it's always f of x minus g. They may switch the names of the functions around, but it's always the top function minus the bottom to make sure when you subtract that you get a positive value for the height. All right, let's go ahead and try this on an example. Let's try and find the area between f of x equals 5x minus x squared and g of x equals x. Let's go ahead and start out by looking at a graph of those two functions. So we'll enter those both in. So we have y equals 5x minus x squared. That's going to be a parabola that opens downward. And then we have the line g of x equals x, which is just y equals x. So a 45-degree angle line. And we'll go ahead and look at the graph. Let's do the standard zoom. So here's our first intersection, and then from here to the next intersection, we're trapping some area between that parabola and the line. So that's the area that we're trying to find. Looks like the parabola is the top function and the line is the lower function. So now, how do you go about getting this area? Well, first you need to know precisely where were those intersections, and you can find those points of intersection by setting the two functions equal to each other. So 5x minus x squared is equal to x. And then just start doing some algebra. If I move everything over to the right-hand side, then I will get x squared. If I move everything to the right, the left side will be 0. That negative x squared will move over as a positive, and I'll subtract 5x from both sides as well. So then I'll end up with negative 4x over here. So then I can factor that by taking an x out, and that gives me x minus 4. And if we were to go back and look at the graph, we'd see that those points of intersection end up at 0 and 4, which we're getting from right here. So this one gives us x equals 0, that'll be A. This one gives us x equals 4, that'll be B. And let's just draw a quick sketch of it over here as well. So the parabola, by the way, if you take this part and factor an x out, you get x times 5 minus x. And that has zeros at 0, 0, and 1, 2, 3, 4, 5. So we have a parabola that opens down, hitting those 2 points, and then we have a line going through at a 45-degree angle, and we know that this point happens at x equals 4. We know that because of our algebra work over here. And we also knew that there's the other intersection at 0, 0. So we're trying to find that area in between. I always like to draw a rectangle. Let's go ahead and do that in a different color. So just somewhere along the way, we'll draw a rectangle and think about we want the area of that rectangle turned into an integral. So let's go ahead and set up what that would look like. The area between those two functions will be a equals the integral from the left boundary 0 to the right boundary of 4. We're not going all the way to 5 because that's not a boundary between the two regions. We're going to end here at 4 because that's where the area is bounded between those points of intersection. We want the top height, which is the y value for the parabola, and the y value for the parabola is 5x minus x squared. And then we subtract the y value for the line, and the y value for the line is just x. So we do that, and that's going to be our exact area. We can simplify that a little bit because we got some like terms in there, so that becomes the area from 0 to 4. And then we have these two guys right here as like terms. So if we combine those, that's going to be 4x minus x squared dx, and then this is a fairly straightforward antiderivative for us to do. So this is going to be the antiderivative of 4x, which would be 2x squared, minus the antiderivative of x squared, which would be x cubed over 3. And then we would evaluate that from 0 to 4. And I'm going to allow us a little bit of a shortcut on these now that we know how to use fnint. As long as you show me the antiderivative step, which I just did, right? So I did the antiderivative and said what needs to be evaluated. You can then go ahead and back up a step to here, enter that into fnint, and just get the answer. So let me go ahead and show you how to do that. So going back over the calculator, we're done with the graph. I'm going to go into the math menu and choose fnint, and then type in that function just before we integrated it, which was 4x minus x squared, and then comma, the variable is x, and the boundaries are 0 and 4. So you enter that in, and you get a decimal. I do want us to give exact answers when possible, so then we just go back into math and choose store to a fraction, and it'll tell us that is 32 thirds. So then I'm going to switch back over and say my answer there is 32 thirds. So you are welcome to do that same shortcut on the homework. And I'll even allow it on tests unless the directions specifically to say to show all your steps. I do want to see you do this antiderivative step so that you stay comfortable with that, but then we'll cut out the tediousness of plugging in the 4 and the 0 and doing all the fraction work, and just take care of that using fnint and stored a fraction. All right, on to more examples. All right, continuing on, our next example is one that we refer to as compound regions. So this is one where the top and bottom function can change as we go through our interval. So find the area between y equals sine of x and y equals cosine of x, and x equals 0 and x equals pi over 3. So let's start out by looking at this visually to see what they're talking about with these compound areas. So let's go ahead and open up the calculator over here on the side. So let's enter our two functions. So we have y equals sine of x, and then we have y equals cosine of x. So cosine of x, and then we also have these other two boundaries, x equals 0 and x equals pi over 3. When they give you boundaries like that, I would just suggest setting that up in your window. So let's go into the window settings, and for our x minimum, we'll set 0. And then for our x maximum, we'll set the pi over 3. So second pi divided by 3. And then sine's always between -1 and 1. So I'm going to set my y minimum as -1.5. And the y maximum is 1.5. And then I should be able to see everything that's going on in the graph. So we'll hit graph now. And there's our two functions. So I forget which one was the red one. Let's see. Y equals cosine of x would be the one that starts out at a height of 1, so that must be the red one, and y equals sine of x is the green one. So it looks like at first, right here, we have the cosine up top, but then once we cross this point right here, all of a sudden now cosine is the bottom. So remember, when we're integrating to find area bounded between two functions, for height we do top minus bottom. So in this region, the top is the red one, which is cosine, but when we get to the second region, the top function is the green one, which is the sine function. So we're going to have to separate this into two integrals at the point where top and bottom switch, which is right here. So we've got to go figure out where that point is. So let's go back now to the notes, and we can draw a quick sketch of what we just saw there as well. So let's do that. So we had the cosine function, and let's see, we can go ahead and match those colors somewhat. So the cosine function came up like this, and then the sine function dropped down and did something like that. And then this was our boundary over here at pi over 3, and our other boundary was 0. So if we do a rectangle right here, the top function is the cosine. But if we do a rectangle over here, then the top function is the sine. So we need to make a switch and do the integrals differently once we cross over this cutoff right here. So let's find out where that is. We find that by setting the two functions equal to each other. So sine of x equals cosine of x. Instead of doing some algebra here, I'm just going to kind of use my memory on this. When does sine x equals cosine x? That's when they're both equal to root 2 over 2, and that happens at pi over 4. So just kind of searching the memory banks for the solution on that one. Now, if you don't like that technique, another thing you could do is divide both sides by cosine of x. These would cancel and give you a 1, and you'd get tan x equals 1, and you could solve that, and that'll still give you the pi over 4 solution. All right, so let's set up the area now. So we're going to do two integrals. The first one is going to be from 0 to pi over 4. And then remember, we wanted to do top minus bottom. And the top, the red one, was cosine, and the green one on the bottom was sine. So as we go from 0 to pi over 4, we're going to do top minus bottom, so red minus green, so cosine minus sine. That's the height, and then the width comes from the delta x, which in integral form becomes dx. That gives us this area right here. Now we still want to find the area on the other side, this area right there. So we have to add on another integral. So we're going to go plus, oops, said pi over 4, I think. I didn't write it though, so pi over 4 was our boundary. So when we do our second integral, that goes from pi over 4 until we reach the end of our interval they gave us, which is pi over 3. And now top and bottom are reversed. So the top function now is the green one, which is sine. So we do top sine of x minus bottom cosine of x. That gives us height, and then times the width, which is d of x. So that's going to be the exact area. When we go to find it, we would just do antiderivatives. So antiderivative of cosine is sine. Antiderivative of sine is negative cosine, so that'll become sine x plus cosine x, and that will get evaluated from 0 to pi over 4, plus antiderivative on the other one. So now we're working with this one over here. So the first antiderivative is of sine. Antiderivative of sine is negative cosine, and then minus the antiderivative of cosine, which is just sine. And then that one is going to be evaluated from pi over 4 to pi over 3. And the good news on this one is they did tell us right off the bat that we can round our answer to 3 decimal places. So we're going to just jump straight into fn int on this one and come back and round our answer to 3 decimals. And we should get a positive, by the way, because we've made sure that each piece is positive by making sure we always did the height as top minus bottom. All right, so let's switch over to the calculator and give that a try. So we're going to go to math and fn int, and our first integral is cosine of x minus sine of x. Make sure you close the parenthesis after each trig function, and then comma, the variable is x, and the limits of integration on the first one were from 0 to pi over 4. So that's going to be our first integral, and then we can just go straight and add the second one. So plus, and then go right back into the math menu and fn int again. And our second one, we had that reversed, so it was now sine x minus cosine x. Again, make sure you close the parenthesis for each individual trig function, then the variable, and then our lower limit on this next one was from pi over 4 to comma pi over 3. So there are our 2 fn ints, and we get 0.462401721. They told us to round that to 3 decimal places, so that'll just be approximately 0.462. So taking that back, approximately 0.462. All right, so let's just go ahead and highlight that answer and move on to the second one. But just a quick comment, I'm happy with you to go ahead and do the same amount and level of work when you're doing your homework problems. Set up your integrals, find the antiderivatives that you need to evaluate, but from there you can go ahead and use fn int and then just get a nice quick answer from there. All right, so now let's move on to that next one. Find the area between y squared equals x, which is a parabola opening to the right. So that is this red curve that's shown on the picture. And then y equals x minus 2, that's a straight line, so that's going to be this one right here. So what makes this one a little tricky is that we have rectangles that don't behave the same way all the way across the region. So our region looks like it goes from 0 over here on the left until we hit this second point of intersection at 4 over here on the right. So our region is that part bounded in between. You can do a quick highlight on that. I'll just do a messy version, but we're just trying to find this area right in here. And again, from left to right, that's going from 0 on the left to 4 on the right. So those are going to be our limits of integration. So now where the issue comes in, if I draw a rectangle over here on the left, when I think about top minus bottom, the top is the parabola and the bottom is also the parabola. But if I do a rectangle over here on the right-hand side, then the top is the parabola, but the left is the line. So if your boundaries are changing, if your height or if your top or your bottom is changing for a rectangle, you've got to make those separate integrals. So where does that happen? It happens right here. That's where the switch happens. So everything before I get to x equals 1 is going to be top is parabola, bottom is parabola. Every rectangle to the right of that is going to be top is parabola, bottom is the line. So we got a little bit of work to do. The first thing is we need to think of the top of the parabola and the bottom of the parabola as separate functions. So you do that by taking the y squared equals x, taking the square root of both sides, which gives you y equals plus or minus the square root of x. So y equals plus square root of x is the top function or top half of the parabola. Y equals negative square root of x is the bottom half of the parabola, so that will be our bottom function. We already have the second one solved for y, so that one's fine. And then we're going to separate this into two integrals. So let's set up the area, and then we'll do antiderivatives, and then we'll find the value. So the first integral is going to go from 0 to 1, where the top boundary is the square root of x, and the bottom boundary is negative the square root of x. From 0 to 1, the upper boundary is the top half of the parabola, and the lower boundary for the height is the bottom half of the parabola. And the width would be dx. So that gives this portion right here. Now we still need to do the part from 1 to 4. So I'm just going to write that as added on. So plus from 1 to 4. The top of a rectangle over here. So now thinking about this rectangle, its top is the parabola. The y value there is equal to square root of x, minus the y value down here from the line, and the y value on the line is x minus 2. And then that's top minus bottom, and then we would still need the dx. So there's the area set up as an integral. Before we evaluate this integral, let's do a little bit of simplification. These two negatives would make a positive, so we'd have 2 square roots of x right there. And instead of writing it as 2 square roots of x, let's write it as 2 times x to the 1/2. And then on our second integral, we can do some similar converting. So we're going from 1 to 4. We'll change the x to the 1/2, and we'll clear the parentheses, so that becomes a minus x and a plus 2. All right, so now let's move on to antiderivatives. So for the first one, that becomes 2x to the 3/2 divided by 3/2, which would be the same as times 2/3 out front, and then that would get evaluated from 0 to 1. And then our next antiderivative would be x to the 3/2 divided by 3/2, or times 2/3 out front, minus x squared over 2 plus 2x. And then that one's evaluated from 1 to 4. All right, so we're going to go ahead and do the same idea as before. We set up the definite integrals. We found the antiderivatives. Now it's time to plug in. And if you want to save time on the plug-in step, you can go ahead and just switch over to the calculator and do fn_int. So that is going to be my next move. So let's go ahead and have a look at that on the calculator. Clear out the last one, math, fn_int. So our first one is 2 times the square root of x. You can type x to the 1/2 if you want, or you can type the square root of x. The calculator doesn't care what form it's in. And we're doing that one from 0 to 1. And then we're going to add on our second math, fn_int. And the function for that one is the square root of x. And then we have minus x and plus 2. The variable is x, and we're evaluating that one from 1 to 4. So let's see. I think I didn't need that parenthesis right there. So we get 4.50002. Kind of interesting, that 0002 part I happen to know is a mistake. This is really just 4.5. So the calculator's got apparently, maybe because of the Simpsons rule stuff going on, it's like not perfect, so it's got a little bit of error involved. This should be as 4.59 halves. I'm curious what will happen if I try to store it to a fraction. Yeah, it has trouble with it because of the extra 0.02. I'm going to throw that away, do math, store fraction. There's our 9 halves. So I've done this one by hand. I do know the answer is 9 halves. So just be aware of that, I guess. There's a little bit rounding error that happens with the Simpsons rule going on behind the scenes when we use fn int. So switching back, we'll go ahead and write that answer as 9 halves. And we see, I guess, a little bit of flaw in our cheater system of using fn int. So you can always evaluate it, by hand the regular way and verify this. But fn int, for the most part, isn't going to cause that problem. So I still would recommend that you give it a try. All right, so this one was definitely messier than some of the others. And why was it messy? Primarily, it was messy because of what happened right there. As we crossed over that intersection between the two functions down below, the bottom of our rectangle changed from being the bottom half of the parabola to being the line. So here's the plan. What if we didn't do rectangles that were vertical? What if we did a rectangle that was horizontal? Notice if we did that rectangle, the right-hand side is the line and the left-hand side is the parabola. What if we go down here? It's still the right-hand side is the line, left-hand side is the parabola. It never goes from parabola to parabola, right? So it turns out if you do it that way, you can do it as just one integral instead of two. So as we turn the page, I'm going to show you how to set that up, and then we'll try the problem again with this horizontal rectangle approach and see that it ends up being a little bit easier. So it's going to be nice to have both of those options at our disposal. All right, let's go ahead and look at that idea of doing an integral with horizontal rectangles instead of vertical ones. So sometimes it makes more sense to integrate with respect to y instead of with respect to x. This is one of those times. So if you're trying to find the region they've shown in this picture and you draw a rectangle like the one that they've got right here, its area is going to be the right side minus the left side to get kind of the height of this tipped over rectangle times the width of it, which would now be a delta y. So this is a delta y now, this vertical height, instead of a delta x. And we can try and work with that. So what if I just did the area of that one rectangle, called that area sub k? Then that would be the right-hand side, which would be the x value over here, which according to this is equal to f of y. So we'd be evaluating that right-hand side at some y sub k star. And then we do the x value on the left, which would be this x value is g of y, so we would subtract g of y sub k star. And then we'd multiply by how tall that rectangle is, which is its delta y. And if we wanted to turn that into the area over the whole region, we would take the sum, as k goes from 1 to n, of that same thing. So of the right-hand side, f of y sub k, let's try that one more time, f of y sub k star minus the left-hand boundary, which is g of y sub k star, times the thickness of that rectangle, which because of the horizontal layout here would be a delta y. So now what if instead of, I put a of k equals, let me fix that up. This part right here is no longer just that one rectangle. We're taking the sum. So now this is actually the full area. And it's not equals, it's approximately equals because it's still just rectangles. So how do we get it to be not approximate anymore? We would add on the limit as n goes to infinity out front. And what happens if we do that addition of the limit onto there? Then it becomes an integral, where our lower boundary is c and our upper boundary is d, and the right-hand side is f of y, left-hand side is g of y, and the thickness is dy. So let's go ahead and read through this box and then try that previous page example again using this method. So this is the area of a region between two curves done with respect to y instead of with respect to x. So suppose f and g are continuous with f of y greater than g of y, which is to say f of y will be on the right and g of y will be on the left. And we're working over the interval from c to d. Then the area of the region bounded by the graphs of x equals f of y and x equals g of y over that interval is given by a equals the integral from c to d of f of y minus g of y times dy. And I mentioned before it's good to be able to do these in words. So zoom in here and say what the words would be. So we're doing the integral from c to d of the right-hand side minus the left-hand side times the thickness, which would be the dy. So same idea as before, but instead of doing top minus bottom, when we do a dy to make sure that we get a positive height for the rectangle, we're going to do right minus left. So let's try and apply that to that problem we did earlier of finding the area between y squared equals x and y equals x minus 2. So as I mentioned on that previous page, if you do a rectangle right about here, right-hand boundary is the line, left-hand boundary is the parabola. If you drop down here to a lower portion and do a rectangle there, right-hand boundary is the line, left-hand boundary is the parabola. Since there's no switch there, we can do it as one integral. But now it's going to be a dy because we're doing horizontal rectangles. So we're going from the lower point of -1 to this upper intersection, which is at 2. So now our limits of integration are going to be the y values instead of the x values. All right, so this area is going to be an integral from -1, the y value at the bottom, to 2, the y value at the top. We're going to do the right-hand x value, and we're probably going to have to pause here for a second. The right-hand x value comes from this equation, so you need to know what that right-hand x value is. So let me move this down here a little bit, and let's work on that. So the right-hand x value, just add 2 to both sides on this, and you get x equals y plus 2. So that's our right-hand x value. Here's our left-hand x value. So our right-hand x value is y plus 2 from the line. Then subtract the x on the left, which would be the x from the parabola. The x from the parabola is y squared. And then with respect to y, that gives us our thickness of those rectangles. So we only have to do one rectangle instead of 2. And let's go ahead and take a look at that. So it'd be from -1 to 2, y plus 2 minus y squared dy. Do antiderivatives, so y squared over 2 plus 2y minus y cubed over 3, and evaluate that from -1 to 2. And if this all works, we're going to get the same answer as we did on the other page, which I believe was 9/2. So let's switch over to the calculator and give this a try. All right, so opening up the calculator and doing this attempt, remember that when you do this, you're entering in the integral, right? So I want you to show me this so that you're remembering how to do antiderivatives to do definite integrals, but for the evaluate part, you've got to plug in the integral itself. So we're going to go math, fn int, and then what was our function? It was y plus 2 minus y squared. You could hunt around for a variable y and use that, but the easiest thing is just to use the variable x, so x plus 2 minus x squared. Fn int doesn't care what variable you use as long as it matches the function and you tell it what the variable is. So you can always switch a variable from anything that was given. It could be x, y, theta, whatever. You can switch it to the x value. And then our limits of integration were from -1 to 2. So if this whole business with the dy method works, we'll get 9/2 just like we did on the previous page. So when I press enter, I get 4.5. If I go to math, convert that to a fraction, I do get the 9/2 again. So let's go back, write that down, and That finishes off this problem. And now, given the choice of the two methods, you should want to choose this one because it was just one definite integral instead of two. And it was actually a lot easier too because you didn't have to split the parabola up into top half and bottom half. So from now on, anytime we're going to find an area, instead of just blindly doing a vertical rectangle and a dx, we will think about what seems like easier rectangles for our region: vertical ones, dx, or horizontal ones, dy. So we'll continue looking at examples as we go to the next page. All right, we're going to wrap things up with one more example, finding the area between y equals x cubed and y equals the square root of x. And we're going to actually just look at this one with both ways, with respect to x and with respect to y. Let's look at a picture real quick and see why it's reasonable to go ahead and do it in either way. So just a quick sketch of this. Doesn't have to be perfect, and then we'll do algebra to work out some of the details. So let's do y equals x cubed as a green graph. So y equals x cubed comes up, flattens out as it goes through the origin, and then curves back up. And then y equals x cubed starts at the origin and is the top half of a parabola, so it does something like this. So we just get this rather small region that we can try and find the area of right here. And if we blow that up, it doesn't seem like it would make too big of a difference whether we did the rectangle vertically, like this, top minus bottom, or we could go horizontally like this and do right minus left. And we should get basically the same thing either way. As you slide those rectangles across, if you're doing the horizontal ones, so if you're doing this version, as you slide that up, the right-hand boundary is always the green graph, and the left-hand boundary is still going to be the red graph. And if you slide it down, right boundary is the green graph, left boundary is the red graph. If you want to go vertical instead, it's going to still be top is red, bottom is blue, top is red, bottom is green, top is red, bottom is green. Over here, top is red, bottom is green. So it's going to be consistent the whole way through, whether you do it with the horizontal or the vertical. So what we're going to do is we're going to start off doing it with the vertical as a dx, and then we'll see how that one goes, what we get, and then we'll try it again with the horizontal. All right, so we need to know where this point of intersection is right there. So we'll try and find that. We need to know this one too, but that looks like 0, 0. So we'll start off by just setting these two equal to each other. So x cubed equals the square root of x. And we want to get rid of that square root, so what we'll do is go ahead and square both sides. And if you do that, you get x to the 6th equals x. You can subtract x from both sides, so x to the 6th minus x equals 0. You can factor out an x, and that produces two different solutions, either x equals 0 or x equals 1. And it's good we found those as x's because we're about to do a dx version, which needs x boundaries. So our left boundary right here is 0, and this right boundary right there, it appears is going to be at 1. Okay, so the area is the definite integral from 0 to 1 of top minus bottom. The top is the red graph, which is the y value from the square root of x. So square root of x for the top, minus the bottom y value, which is the green cubed function, so y equals x cubed, and then the width of our rectangle is dx. So just doing a little color coding here. The red function was y equals the square root of x, and the green function was y equals x cubed. So we did the x cubed for the bottom, and we did the square root of x for the top because that's the arrangement on the graph that we have over there. All right, and then in terms of just finishing it off, that x square root of x is x to the 1/2, so that becomes x to the 3/2 divided by 3/2, or times 2/3, minus x to the 4th over 4, So that's our antiderivative being done. And then we would evaluate that from 0 to 1. So at this point, I'm going to go ahead and put that into fn int to come up with a value. But again, just a reminder, when you go to fn int, you're putting in the definite integral. So this is what we're going to put into fn int. This is just for us showing our sharpness on doing antiderivatives and that we know how to do this by hand. Now let's go to the calculator though and get a little assistance on that last part. So math, fn int, and then enter what we were doing the integral of. So it was the square root of x, and this parentheses on the square root, minus x raised to the third power. Our variable is x, and our limits of integration were 0 and 1. So this is what we get, and then we can go math, store fraction, and see what that is. Well, it's not being very kind to us here. I'm going to try this again. It's 0.41. It's actually just a ton of sixes, and then a 7 eventually when you round it. Let me try storing that to a fraction. So 5/12, which is correct. So what's going on there? Like, why did we get that 6767 at the end originally? Again, that has to do with like the Simpsons rule not giving us the exact value. It is an approximation method. Apparently this calculator should just be using a higher value of n. I think you'll be okay on your actual TI-84 and not have the problem I've been having where it's not giving you the exact answer and giving you some conversion problems. But it is going to be 5/12, so you could verify that by hand if you want to go work through that. All right, so there it is as a vertical rectangle. So now what I want to do is try the same exact problem again, but with respect to y. So when we do it with respect to y, we're going to want to say that the area is equal to the integral, and we'll have to find our limits of integration. So I'll just write c to d right now. We usually use c to d for the y values and a to b for the x values, just to remind us that it's a different letter. And when we do it as a dy, we're going to do right-hand side of a rectangle minus the left, and then the thickness of that rectangle will be a dy. So in order for that to work, you've got to figure out a couple things. What are the boundaries for the y values? And then also you need your function to be x equals, because your right-hand side is the x on the right, and the left-hand side is the x on the left. So let's draw the picture again. I'm going to blow it up a little bit better this time. So just want to match the colors. I believe I did green for the cube function, so that came in, flattened out, and went up. And then our y equals x cubed, or y equals the square root of, y equals the square root of x function did something like this. And we have this point of intersection, and we have that point of intersection. So we know that the x value here was 1. If you want to know the y value, just plug that into one of the original functions. So I'm going to copy one of them down here, y equals x cubed. If you plug a 1 in there, you get 1 cubed, which is also 1. So our upper boundary as a y value will be a 1. And this one you can see is the point 0, 0. Before we were using the x of 0, now we're going to use the y. Because this time we're going to look at a rectangle that lays across. So we need to know what this x value is in terms of y and what this x value is in terms of y. So for the green one, let's take this and solve for x, because that's the green function, right? So take the cube root of both sides, and you'll get the cube root of y is equal to x. Our other function, use this space down below, our other function was y equals the square root of x. And let's work on that in red. If you square both sides, you get y squared equals x. So our right-hand function is this x value right here, which is the cube root of y, and our left-hand boundary is right here on the red function where x is equal to y squared. And our lower limit in terms of a y value goes from 0 to our upper y value at the other point of intersection, which is a 1. All right, so back to work on this. This is going to be the integral from 0 to 1. This time these are y values instead of x's. It's a little unfortunate they're the exact same values in terms of the number, but we are looking at the y's this time. The right is the x value for the green function, which is the cube root of y, minus the left-hand side of our rectangle is the x for the square root function, which when you solve that one, you get x equals y squared, so minus y squared. And then with respect to y. Antiderivatives, this cube root right here is y equals 1, y to the 1/3. So that'll become y to the 4/3 divided by 4/3, or times 3/4, minus the antiderivative of y squared, which will be y cubed over 3. And all of that will get evaluated from 0 to 1. I'm going to go ahead and enter that into fnit to get the answer. But remember, when we enter into fnit, even though we're practicing doing the antiderivative work, it's the definite integral that we have to type in. This is the exact same area we're finding here as we did on this problem up here. We're just doing it with a horizontal rectangle instead of a vertical one. Should still be 5/12 though for the answer if everything's working right. So let's go to the calculator and see. So clear out all that stuff. We're going to do a new math and fnint. And this time we have the cube root of x. So I'm going to do x raised to the 1 divided by 3 minus x squared. And yes, I know they were y values, but again, it's easiest if you convert your function over to an x when you type it into fnint. So I'm using the variable x, and I'm going from 0 up to 1. Doing the same area, so I expect the same answer. And I get the 0.416667. And let's see if the convert to fraction will be kinder to us this time. Yes, 5/12. All right, so there's our answer that we expected. And we did it with the different technique, got some more practice with the horizontal rectangles. So just a final note here, it really doesn't matter which way we did this problem. So we could do it as the dx, and it was fairly straightforward. We could do it as a dy, and it was fairly straightforward. So our decision to do dx, dy doesn't matter on this one, so I'd probably just do a dx because it's what we're more comfortable with. But if you go back and look at this one, where we did the horizontal rectangle, compared to the previous page where we did the vertical rectangles, sometimes it makes a big difference. So before I do a definite integral, I always try to visualize what would vertical rectangles look like. Would the boundary be consistent, or would I have to break it into two integrals? In this case, because the lower boundary changed right here, I had to break it into two integrals. Whereas if I did it as a horizontal rectangle, we didn't get a boundary change and we could just do one. So it's problems like that where you really gain the benefit of doing the dy method. So just give this some practice, get used to it both ways. As we go on to the next sections in the book, we're going to do more dy problems, so we'll get more practice with it. But here's a couple examples. Hopefully that's helpful. Good luck as you go into the homework. That wraps up section 6.2.